Okay, good morning, everyone. Let's dive in. Any questions about the assignments? So far, so good? Ticking along? Okay. All right, so back to our history of evolutionary robotics. Started in the mid-90s. Since then, it's sort of headed off on two different branches. The first of these two branches is what we're looking at this week, the subfield of minimal cognition. Boil down our embodied agent to a minimal set, a minimal body, minimal brain, and let's see what kinds of building blocks of cognition we can evolve into those machines. And then next week, we'll switch to locomotion and talk about creating machines that get from point A to point B, arguably, if not the first, one of the first building blocks upon which all other cognition is built. Yeah? In the experiments we're looking at in lectures 9 and 10, all of the robots there were evolved using CTRNNs. We talked about those last time. They have various advantages over traditional neural networks. When we finished lecture 8, the CTRNN lecture, we looked at the robot that shook the block up and down and left and right and forward and back. That robot was evolved to exhibit one of the building blocks of cognition, which was compositionality of motor primitives, right? You learn very short, simple movements and then compose them together hierarchically into more and more complex behaviors that unfold over time. So that was sort of the first building block that we looked at. In lecture 9, which hopefully we'll get all the way through today, we're going to look at 4 different building blocks. And we started by looking at the first of those 4 building blocks last time, which is looking at the world around you, identifying various objects in the world. And why are we interested in the objects around us? Because we can do things with them. When we look at objects or we touch objects, doesn't really matter whether we see here or feel them, they project affordances. They advertise how we can interact with them. Affordances, as we saw last time, depends not just on the object, but depends on the embodiment, the morphology of the agent themselves, right? You have to have a certain body plan to be able to recognize that you can sit on these objects and they will support your weight. Yeah? Okay. How do we train a robot? How do we evolve a robot to recognize affordances? In this particular paper, from which we're going to draw these 4 experiments today, they evolved robots to detect a particular affordance, which is passability. Most affordances end in ly. Or le. It's passable, it's impassable, it's graspable, it's not graspable, it's sittable, it's not sittable. Another way to think about affordances. Okay. These are minimal cognition experiments, so they tried to boil this down to as simple a task of object detection, affordance detection as possible. The agent itself is very, very simple. It's a square. It exists inside a 2-dimensional physics engine. It sits at the bottom of the screen, and our little agent here has 7 sensors, represented by the gray lines here. These are proximity sensors like we've seen before. They're projecting up in this 2-dimensional world, and at every point in time, our little square agent here, our little square robot is getting back 7 numbers, which are the lengths of these 7 beams, 7 sensors, and it's got 2 motors. You can think of these as little rockets, if you like. At every point in time, the neural network, the CTRNN, controlling this robot is outputting 2 numbers, which is the force of the left rocket and the force of the right rocket. So when this robot starts to move, it's going to move left and right along the bottom of the screen. You may or may not remember one of the very first video games, Space Invaders from the Stone Age, yeah, right, moving along the bottom of the screen. That's basically what we've got here. They're going to test this robot by dropping pairs of objects above it, and these pairs of objects are going to have varying widths between them. The task for the robot is to quote-unquote see this pair of objects and detect the affordance advertised by this object pair, which is whether the gap between the pair is passable by the robot or not. If the robot positions itself directly underneath this pair of falling objects, will it be able to pass through them, or will the objects fall on either side of the robot and not hit the robot itself? That's passable. If the gap is overly narrow, what do you think the robot should do? Get out of the way, right? So they're going to, that's the idea. That's what they want to evolve the robot to do. So they're going to construct a fitness function that rewards or selects for this behavior, selects for affordance detection. Yeah? They're going to start by creating a population of random CTRNNs. So CTRNNs with different tau values, different Ws, different thetas, different bias values. You're going to take each random CTRNN and plug it into the robot and evaluate the robot a number of times in different environments. They're going to place the pair of objects above the robot at differing widths, allow the pair of objects to fall, see how well the robot does with that CTRNN, reset the whole environment, do it again with the same CTRNN, and ultimately compute P, which is the average performance, or the average fitness, if you like, of that CTRNN at enabling the robot to perform affordance detection. So far, so good? So up here, they're taking the summation over num trials, so the number of trials that they perform with a single CTRNN, and they're going to take the average performance. The performance of the robot in the ith trial is P sub I, and they're going to compute P sub I using a conditional, an if statement. So there's two possible environments. There are environments in which the aperture or the gap between the pair of objects is too narrow for the object to pass through, and they're going to compute P sub I using this. In that case, if the aperture is wide enough, if the affordance is passable, they're going to use this equation to compute P sub I. There's a typo in the paper. There's a third case here, 0. Yeah. Question?
Why would the fitness be lower if it successfully avoids too narrow of a gap rather than colliding with the wall?
They're going to maximize P sub I. So P sub I should be high when the gap is narrow and the robot runs away. Yeah?
Right, but doesn't it say 0 if beyond blocks?
This is for the case when the aperture is wide
Oh,
enough.
I see.
Yep. Yeah, it's just kind of, these are the two conditionals. So basically, you could rewrite this as an if statement. Yeah? Okay, so let's look at the first case. So the pair of blocks are falling, and the gap between them is narrower than the width of the robot itself. Yeah? Okay, so if the robot hits either wall or hits either block, that's not a good thing. Basically, that's indicating that the robot couldn't make up its mind. It was either trying to get through the gap or not quite run away. Whatever it was doing the wrong thing. So we're going to give it a lower value if that happens. If it doesn't hit either of the blocks, we're going to give it maximum points, 100 here. Yeah, it did the right thing. It ran away. Yeah. Remember, we're trying to maximize P sub I, so we're obviously trying to maximize D sub I, which is the horizontal distance between the center of the robot and the center of the gap when the pair of objects gets to the ground. Why are we maximizing D sub I? So the pair of objects is falling, the gap is too narrow, the robot hits one or both of the objects.
The larger D sub I is in that case, that means it made a decision earlier that the gap wouldn't be large enough for it to hit through?
Absolutely. So if two different CTRNNs in the population both cause the robot to get hit, the one that caused the robot to get hit further out from the center of the aperture gets a better fitness, a higher fitness, because although it still got hit, it's at least heading in the right direction. It's moving away from the center of the pair of objects. Everybody see that? There's another typo in this paper. You don't need to take the absolute of a distance, because a distance is always positive. They're a little sloppy with the math in this paper. Okay, so far so good? Okay, so if we're evolving populations of CTRNNs, and over evolutionary time, the P sub I, in this case, gets larger and larger and larger, that means the CTRNNs are evolving to cause the robot to move away from the pair of objects when the aperture is too narrow. You can probably see where this is going. In the other case, if the aperture is wide enough for the robot to pass through, if the robot is beyond the pair of blocks, either far to the left of the blocks or far to the right of the blocks, when the blocks get to the bottom of the screen, that's the worst possible thing you can do, 0, right? This indicates robots that ran away when they should have tried to get underneath the pair of objects. Yeah? If the robot is between the blocks, when the blocks come down and it doesn't hit either of the blocks, maximum points, the robot did the right thing. If the aperture is wide enough for the robot to pass through and it hits one of the two objects, we're going to compute p sub I using this. And there's a little bit to sort of wrap your mind around, so let's start from the inner part of this equation and work out. They're taking the negative of the distance. The negative of the distance between the robot when the pair of objects gets to the ground and the position of the pair of objects when it gets to the ground. We're maximizing or minimizing d sub I. Minimizing, right? We want d sub I to be as small as possible. Yeah? Okay. So, typical evolutionary robotics experiment, they create a population of random CTRNNs, take each one, evaluate it num trials time, compute p sub I for all of those num trial cases, take the average of all those p sub I's, assign p to that CTRNN, take the second random CTRNN in the population, rinse and repeat until you've calculated p for all the CTRNNs, delete the CTRNNs that have lower values of p, and make randomly modified copies of the surviving CTRNNs and repeat, repeat, repeat over evolutionary time. At the end, you take out the CTRNN that had the highest p. At the end of the evolutionary run, you take out the CTRNN that had the highest p, and if you plug that evolved CTRNN back into the robot under a lot of different environmental conditions, what do you think the robot's going to do? What should the robot do? Recognize when it can go through the gap and when it can't. It has no language, it can't tell us. It doesn't say passable or impassable. How do we know whether it correctly recognized or not?
Because it'll do it.
It'll do it, right? It's not going to tell us that it's detected the appropriate affordance. It's going to show us through behavior. Yeah. This was over 20 years ago now, so no YouTube videos, I'm afraid. We're going to have to look directly at the data. My apologies. Okay. In the 4 experiments we're going to see today, they did evolution, and at the end, as I just mentioned, they took the most fit CTRNN out of the evolved population at the end, and then they exposed that evolved CTRNN to a lot of different environmental conditions, some of which that CTRNN never saw during evolution. Yeah? In this case, on the horizontal axis here, they played back that CTRNN thousands of times, where they dropped pairs of objects from the top of the screen with relative aperture widths that were negative, meaning the width of the aperture was less than the width of the robot, or a positive aperture width, meaning the aperture width was wider than the width of the robot. And in all of these thousands of conditions, they measured the final horizontal separation between the robot and the center of the pair of blocks when it got to the ground. Yeah? How did this evolved CTRNN cause the robot to behave? Did it do the right thing? I see a lot of nods. How do you know that it's doing the right thing? How do we interpret this figure?
When the aperture is large enough to fit through, it gets very, very close to the center point between the 2 blocks. When it's not big enough to fit through, the robot clearly goes pretty far away from the center point.
Absolutely, right? So on the right half of this figure is showing all the conditions when the aperture was passable. And in most of those cases, the final horizontal separation was near 0. The robot was more or less between the center of the blocks. The left half of this figure, these are all the conditions in which the aperture was impassable. And in all these cases, the final horizontal separation between the robot and the center of blocks was big. The robot ran away. Did it do what it was supposed to do in every case? Not quite. Where is it doing the wrong thing? Arguably the wrong thing.
Potentially the boundary case.
The boundary case. So near the center here, this is where the aperture is exactly the same width as the robot, or in this case here, this one is kind of interesting, the aperture is just wide enough for the robot to get through. What is the robot doing in these conditions, this edge case, boundary condition? This is obviously the difficult case, right? It's hard to tell. Can I get through the gap or not? What is the robot doing?
A lot of times it's not lining itself upright.
It's not lining itself upright. So if we look at this black dot here, most of the time when the aperture width was exactly the width of the robot, which is impassable, most of the time the robot runs away, but sometimes not. So these vertical lines that are attached to the black dots here, the black dot is the average behavior the robot did in those conditions. The vertical lines are the error bars, showing sort of there's actually a spread of behaviors. There's different things that the robot did in those cases. Most of the time, on average, it ran away, but sometimes down here, it was actually close, and maybe a little bit too close. It might have hit the edge of one of the blocks. What's happening in this case? The aperture is 0.1 units wider than the width of the robot. What's the robot doing in these cases?
Sometimes it moves out of the way and sometimes it doesn't.
Absolutely. So if you look at the error bars here, they're kind of spread along almost the entire vertical range here. So there's sort of all different behaviors here. Down here, sometimes when the aperture was 0.1 wide enough, the robot ran away. And sometimes up here, when the aperture width was 0.1 wider than the robot, it would feel brave and try and thread between the object pair, right? I said it's arguably doing the wrong thing. It's not optimal here. It's making a few mistakes, but it's arguably also doing the right thing. It's kind of erring on the side of caution, right? If you don't know, run away, right? This is an interesting behavior that you see in nature as well. Animals, including us, don't always make optimal decisions. We often err on the side of caution. We make more mistakes than you would expect an animal, an organism, or a machine to do if it was evolved to do the right thing in every case. You make the mistake by assuming the more danger than is possibly there, or maybe assuming less opportunity than is actually there. Generally speaking, if you want to survive long enough to produce offspring, generally it's a good thing to sort of err on the side of caution.
Could you also kind of tweak that cautionary behavior with your fitness function?
Absolutely, right? So we could decide that this is not what we want. We want the robot to be a little bit more risk-loving, to be a little bit more adventurous. We could, and this is maybe a good exercise to try, you could alter these equations that would exert more selection pressure during evolution for doing the right thing, for minimizing these kinds of situations down here. Yeah? It's kind of interesting that I don't know, but it doesn't seem like they did too much tuning of the fitness function. And again, they got back something that's not optimal, but something you also see in nature. Yeah? Okay. All right, let's try and analyze the behavior of this one evolved CTRNN, again, under a lot of environmental conditions. What exactly is the CTRNN causing the robot to do? Let's start by looking at this upper left panel over here. This upper left panel, this is going to be evaluating that single evolved CTRNN in a bunch of environments in which the aperture is impassable. The aperture width is narrower than the width of the robot. You'll notice that the horizontal axis here is horizontal position, and the vertical axis here is vertical position. So it takes a little bit to see how to read this figure. Let's travel up to the very top left of this panel up here. This corresponds to the condition in which there's a pair of objects placed 140 units above the robot, and the robot is placed at the bottom of the screen such that the pair of objects is 40 length units to the left of the robot, minus 40. Yeah? So at this point in time, at this point in the plot, pair of objects is 140 units up and 40 units to the left. Everybody see that? And then they let the pair of objects start falling. Up here in the upper right of this panel, the pair of objects is again raised to 140 length units, and then the object pair is moved 40 length units to the right of the robot, and they drop the pair of objects. As the objects start falling, obviously the vertical distance between the pair of objects and the robot starts decreasing along the vertical axis here. And as the robot starts moving at the bottom of the screen, the horizontal distance, or difference should really be, because we've got negative numbers here, the horizontal difference between the horizontal position of the robot and the horizontal position of the pair of objects is also changing over time, yeah? Which is reported in this figure by these black trajectories. Everybody see that? Questions, comments? Okay, let's follow one of these trajectories to see what the robot did. When the pair of objects the aperture was impassable and the objects were above and to the left of the robot, what does the robot do as those objects start falling? How does it move? Did you have an idea in the back? No?
Like moves underneath the blocks.
At the beginning, what does it do? At the upper part of this figure, what's happening?
The robot doesn't move and just thinks about it.
It's not moving and it's thinking about it. We'll put our scare quotes around everything here, right? When the line is more or less vertical, that means that obviously the objects are falling, and the horizontal distance between the robot and the pair of objects is not changing, which means the robot is not moving. I forgot to mention, the pair of objects always falls perfectly vertical. The pair of objects never falls diagonally. Forgot that detail, yeah? So at least in this case, for 40 units, it lets the pair of objects fall 40 units down before anything starts to happen. It's not perfectly vertical, so the robot's moving a little bit. When the object pair gets to about 90 length units above the robot, what starts happening? The robot starts moving to the left, right? The object pair is to the left of the robot, and the horizontal difference between the pair of objects and the robot starts to approach zero. The robot is moving to the left. It is starting to move underneath the object pair, yeah? So here we go. Robot doesn't do much. Now it starts moving to the left, moving to the left, moving to the left. And when the object pair is about 50 units above the robot is directly underneath an impassable aperture. What does the robot do at that time? We got to keep following this black trajectory. It runs away. It keeps going to the left. It pauses for a moment and then keeps going to the left, and the object pair eventually falls and hits 40 length units to the right of the robot. Everybody see that? Same thing if we drop the object above and to the right of the robot. What happens in these two trajectories here when we drop the impassable aperture almost directly above the robot?
It like kind of moves past it and then back to it to like kind of scan it, I think.
It's moving back and forth underneath, right? Let's follow this trajectory. Back and forth, and then runs away. Yeah, sort of back and forth.
It seems like this robot's algorithm needs the object to be out of its way first so that it can place itself directly underneath it and then run away.
Maybe you're right. What's not shown in this figure, and it's hard to tell, is how good is its vision? How long are these beams, right? It might be that the robot can't actually see the object pair until the object pair gets close enough. Yeah, not quite clear at this point. but it looks like it's sort of sweeping its proximity sensors underneath the undersides of the pair of objects, right? At least when the pair of objects are directly above it. Yeah? Same CTRN, same robot brain. We're going to drop it back into the robot a whole bunch of times, but now we're going to drop the pair of objects again above the robot at different horizontal offsets, and now the aperture is passable. The robot can easily get between the pair of objects. What does the CTRN cause the robot to do under these conditions?
It's like the same thing, but it doesn't run away. It senses if it fits.
Same thing. So the top half of this panel is the same as the other panel. So up until about whatever this is, 50 units, the robot is doing almost exactly the same thing as it did when the aperture was impassable. But then, it gets underneath and stops moving. All of these trajectories are vertical. The robot is showing off. It's there early and waits for the pair of objects to fall on either side of it. Yeah? When did the robot know whether the aperture was passable or impassable?
When the blocks falling, or about 40 vertical units.
Okay, there's a vote for 40 units above the robot.
It's possible that it happens earlier than that, because in the case where it's not wide enough, it always maxes out the horizontal position, so it looks like it can travel fast enough to achieve maximum fitness in that case.
It absolutely could. Again, remember, evolution is a satisficer, not an optimizer. There is probably a set of weights and tau values and biases and gains that would cause the robot to get there early and wait. Yeah?
I'd say between like 50 to 70.
50 to 70, okay? Other votes or ideas for when the robot knows whether the aperture is passable or impassable. At what point in time or vertical distance did the robot detect the affordance? Thinking about thinking is misleading. It's not quite clear. The robot might know much earlier than this, right? It might just not be showing us that it knows until whatever it is, 60, 50, 40 length units. There might be some difference in the values of the neurons inside the CTRNN in these two cases, but that difference is not having an appreciable influence on the motors of the robot yet. Maybe that difference starts to then accumulate, and over some threshold, it does start to affect the motors, and we start to see difference in behavior.
Could you lower the motor speed to try to get it to make a faster decision?
Absolutely, we could hobble the robot in some way. We could slow the motors, for example, to force it to try and make a decision earlier. And in the third of the 4 experiments we're going to see today, they do hobble the robot, not in that way, to see how it responds. Yeah? Okay. I love this paper because they were very analytic. They really drill down to try and understand as best they can what's going on in the head of the robot. So or the head of the CTRNN. So they took, again, same CTRNN. Now they played it back inside the robot tens of thousands of times. And we're going to look at this panel in the lower left here. Every pixel in this panel corresponds to one evaluation of the CTRNN inside the robot. The horizontal position of the pixel represents what the initial horizontal position between the robot and the pair of blocks was, right? Did they drop the pair of blocks above and to the left of the robot or above and to the right of the robot? The vertical position of any one of these pixels represents an environment, reports the aperture width of the pair of objects in that environment. Everyone see that? So tell me about the environment represented by the upper rightmost pixel. At the start of that simulation, what would you see?
The 2 blocks that were falling would have had a large aperture, like a large gap between them.
It would have a gap that's 4 distance units wider than the width of the robot. Yep, that accounts for the vertical position of the pixel, and
40 units to the right.
40 units to the right, and then they drop it. Everybody see that? Okay. So they simulate all of these environments, and at the end, they calculate P sub I, how well the robot did in that environment, and then they color the pixel based on what the robot did. They paint the pixel white if the robot did the right thing. They paint the pixel black if the robot did the wrong thing. It ran away when it should have stayed, or it stayed when it should have run away. And gray represents mediocre behavior. It hit one of the two blocks. In neither of the two cases, passable or impassable, should the robot ever touch the blocks. Yeah? Tell me about this evolved CTRNN. How is it doing in general?
It's doing really well at avoiding the blocks when the aperture is too small.
It's doing really well at avoiding the impassable aperture. So the lower half of this panel is all white, right? The lower half represents all the impassable cases. The robot always did the right thing. Run away. Err on the side of caution. The upper half of the panel represents all the cases in which the aperture was passable. What's happening here?
It's like it does well if it can just barely fit, or if it can like absolutely definitely fit, but like in between those two, it seems to fail.
Yeah, true. So most of the time it's doing okay. It's making some mistakes just above y equals 0 here. Cases where the aperture is just a little bit larger, a little bit wider than the robot, which we already saw, right? It's kind of a scaredy cat here. It's another version of the coward. Kind of runs away if it's not sure. That accounts for this band down here. There's also a whole bunch of gray up here. So there are cases in which the aperture was much wider than the robot, and it still ran away. It didn't necessarily run away. Well, it ran away enough that it hit one of the two blocks. And then there is this black vertical line here in the center. What does that represent? What's the vertical black line represent? It's doing the wrong thing.
When the blocks start right above the robot.
Exactly. When the pair of objects is directly above the robot, aperture is super wide, the robot should just stay. It's in the right place. Yeah? It doesn't. It runs away. Why do you think that's happening? Why is there a whole bunch of gray and black here? Why is this panel not all white?
From the position graphs up top, we see that it scans across the blocks, and maybe it scans across both of them before it turns back. So if it starts in the middle and moves in one direction, it only sees one of the blocks and then keeps going.
It's possible. You'll know if you look at the sensors here, whether it sees one or two objects. Usually, if it's anywhere near the blocks, any appreciable, any relatively small horizontal offset, it sees not just one but both. So this robot can actually see very well. It's looking at these pair of objects. Not that it can't see them. Which kind of makes this a little bit more mysterious.
In the two graphs above, why is there like a white gap at the very top? Like that's the middle case that we're talking about, but there's like a gap there.
Exactly, that's the hint. During evolution, while they were evolving these CTRNNs, remember they evaluated the pair of objects multiple times. These are the multiple times. These are where they placed the blocks at the top of the screen. During evolution, none of the CTRNNs ever saw a condition in which the pair of objects was directly overhead and 140 units up. The CTRNNs definitely did see cases in which the pair of objects were directly overhead, but at less than 140 length units. So the CTRNNs had a lot of experience of being directly underneath the pair of objects, but they never saw during evolution these exact cases. The pair of objects is 140 units directly overhead. Yeah? So what you're seeing in this case is most of the environments in this panel were environments that the robot never experienced, or the CTRNN or its parent or its grandparent or its great-grandparent ever saw during evolution. It's not that surprising. It doesn't always do the right thing, right? We are experiencing environments in which our ancestors never experienced before, and we are trying to do our best, yeah? Not an easy thing to do. We can't evolve organisms or machines in an infinite number of cases. We have to choose what is a representative sample of the things the machine might experience after deployment, during training or evolution. And one of the big unanswered questions in AI and robotics as a whole is what? What are those environments? What is a representative set? Hard to say. And if you get it wrong, you'll get situations where your machine doesn't just do the wrong thing, but it does the wrong thing in environments in which it seems like it was obvious what it should have done, right? These are kind of maybe expected mistakes. If you're not sure, run away. Okay. The aperture is 2 or 3 times wider than you are, and you hit the object, or you ran away when you shouldn't have, yeah? These are worrying situations for AI and robotics in general, yeah? Even environments after evolution or training, we deploy a machine out into the real world. It experiences what seems to us to be a familiar or obvious environment. It's obvious it should know what to do in that situation. Not always the case, yeah? Okay, let's move on to the second of the 4 experiments. Let's look at a different building block of cognition. We've actually seen this building block already. This is something that we as infants, one of the first things you started to figure out, which is when you look out in your world, what stuff is you and what stuff is not you, otherwise known in cognitive science as self, non-self discrimination. Where did we see this before?
Like blind robot that couldn't see with the fruit.
With the fruit, that's right. So we saw cog. It wasn't that it was blind. It was partially blinded. All it could see was motion or lack of motion. And it learned what self is. Self was defined for cog, or cog defined self as the stuff in which when I send commands to my motors, stuff moves. And when I stop sending commands to my motors, that blob of motion stops, yeah? Here's a minimal robot that evolves the ability to distinguish between self and non-self. In this case, we're going to glue the robot to the bottom center of the screen. We're going to give it an arm and a hand, and it can wave that arm or rotate that arm above itself. And we're going to drop, in this case, a single object at the top of the screen. This object might fall straight down, it might fall at a diagonal, it might fall slower, it might fall faster. However this object is going to fall, it is going to land near the robot. Somewhere the object is going to pass or break this semicircular dash line somewhere. The robot has to move its arm such that it catches the object at that point. Yeah? Pretty simple task. So where does the self, non-self discrimination part come in? You'll notice in this cartoon here, it's got this little circular hand. And like before, this robot has 1, 2, 3, 4, 5, 6, 7 gray beams, proximity sensors, emanating out from its body. In this case, the first and the second beam, it's just the first beam here collides with the object. So the robot at this point, snapshot in time, the robot sees this external object, and it also sees its own hand. The 5th and the 6th proximity sensor are reporting high values. They're being blocked by the robot's own hand. Yeah? Okay. So the robot, remember, is only getting back 7 numbers at every point in time. How does it know whether it's looking at an external object, its own hand, neither, both? It's going to have to figure this out because it has to pay attention to the object. It has to not just see the object, but infer where that object is going to hit and rotate its arm to get there. Make sense? Okay, so similar to what we saw before, this robot has 7 sensors. In this case, it has just one motor that rotates its arm. Fitness function, like before, we're going to drop for a single CTRN, we're going to drop a whole bunch of objects, num trials times. We're going to see how well, on average, the robot does on quote-unquote catching the object. Its hand has the same position as the object when the object gets to the robot. And we're going to compute P sub I, how well the robot does in the ith trial, using theta sub I here, which is the angular error between what is the angle of the object relative to the robot when the object gets to the robot. What's that angle? And what's the angle of the robot's arm? And we're going to take the difference between these two angles, which is an angle. Yeah? Do you want to maximize that angle or minimize that angle? Minimize it, yeah? So it's on the, again, don't worry about the rest of this for a moment. The theta is to the right of a minus sign, yeah? So the best possible thing the robot can do is the best possible thing that a CTRN can cause the robot to do is get a theta sub I of 0 in all num trials, yeah? So another typo in the paper itself. This should be min rather than max. So if theta sub I is 0 in all the cases, we're going to get a P sub I of 1 minus 0, which is 1. So in this case, 1 is the best possible P sub I value that the robot can get. Yeah? So in order to do well, the robot needs to minimize theta, but to keep us sane here in all these experiments, we're always trying to maximize P or maximize fitness. So we put it on the right-hand side of a negative sign. The fractions are just to kind of normalize this so that the P sub i's lie somewhere between 0 and 1. So far, so good? Okay, same thing as before, create a population of random CTRNs, evaluate them all, compute P for all of these CTRNs, delete the CTRNs that have lower P and make randomly modified copies of the CTRNs that survived, continue evolution, continue evolution, continue evolution, and after a while, you stop the evolutionary algorithm, pull out the CTRN that has the highest P, and again, they're going to play back that CTRN many times in the robot under different environmental conditions, yeah? Which is reported down here. So on the horizontal axis here, this represents a whole bunch of different environments in which the final object hit minus pi over 8 radians above and to the left of the robot, or plus pi over 8 radians to the right of the robot, or the object hit this semicircular dashed line directly above the robot. Yeah? So the horizontal axis here is reporting where in radians the object landed. And the vertical axis is representing, again, in radians, where the robot's hand was. How did the CTRN do under all these different conditions? I see a bunch of thumbs up, right? Generally speaking, whatever the final object angle was of the object, the arm had more or less the same angle. You do see the error bars here, which are these vertical bars. There's a little bit of error here. Under different conditions, the robots do it. It doesn't exactly grab it, but it gets its hand pretty close, yeah? Most of the time. Pretty good, not perfect. Okay, this is the trickiest figure in this paper to digest, so we'll take a minute or two to figure this out. Like we saw in the previous experiment, this visualization was designed to show you exactly what the robot did in a whole bunch of different conditions. Yeah? Okay, here we go. You'll notice there's a whole bunch of wavy trajectories. If you take any point on this trajectory, the horizontal position of that point represents where the arm was rotated to. So you look at if we look at these trajectories over here that are over to the left, these represent cases in which the arm the robot had rotated its arm to the left. These trajectories up here correspond to cases in which the robot's arm was to the right. If we go back to these trajectories on the left, in these cases, the robot started with its arm at minus pi over 8 radians, and then when the object started falling, it actually rotated its arm even further to the left, but then started to drag its arm back, and in some of these cases, it rotated its arm all the way to pi over 8 radians, and then even further to the right, zigzag, zigzag, zigzag. The vertical axis, like before, is representing time in the simulation and also the vertical height of the falling object. Each individual trajectory here is corresponding to a different dropped object. In all of these cases, we'll come back to the color of the grayscale of the trajectory in a moment. Let's just focus on the position of these trajectories. In all of these cases, the trajectories ended at 0 radians. What does that tell you about the robot? What was the robot doing at the end of all of these simulations?
Catching the object. Or going.
We don't know where the object is. It's just the position of the trajectory is telling us about the robot's arm, the position of the arm. What was the robot doing at the end of all these simulations? Bringing its arm to the middle, right? So in all these cases, right at the end of the simulation, the robot always had its hand straight up, 0 radians. So far, so good? It does actually catch all the objects, because in all these environments, they're going to drop the object from different positions and falling at different angles. But in all those different cases, the object is actually falling so that it will land or pass directly overhead, right? So the robot actually successfully catches all of these objects. Yeah? Question?
Would you evolve it such that it doesn't just know to go to the middle?
This is showing a subset of environments in which the object always hits overhead. If the object hits or passes just above and to the left of the robot, in most of the cases, this C-turn N gets the arm to the right place.
This is just like a subset of the training.
This is a subset of the environments. Okay. That's right. Okay, so far so good? All right, let's talk about the color or the grayscale of the trajectories. The color of the trajectory represents the initial position of the object. Where was it at the top of the screen when the simulation started? Light-colored trajectories correspond to objects that were placed above and pi over 8 radians from the robot. So if you were to draw a line from the object at the top right of the screen down to the robot, which is at the bottom center of the screen, that angle is pi over 8 radians. The dark-colored trajectories correspond to cases in which the object was placed above and pi over 8 radians to the left of the robot. You'll notice there's a gradation or a continuous change between black trajectories and very light-colored trajectories, which means they're dropping that object from a whole bunch of different horizontal positions at the top of the screen. So far, so good? Okay, let's consolidate our intuition about this. Let's follow one of these trajectories. Let's take this trajectory up here on the left, the light-colored trajectory. The fact that the trajectory itself, the position of the trajectory is to the left, means that the robot started with its arm above and to the left. So the investigators, when they started the simulation, they actually cranked the robot's arm to minus pi over 8 radians. This trajectory is light-colored, means that they placed the object above and to the right of the robot. So if you can, I want you to visually track this light-colored trajectory all the way down to the bottom of the screen. It's a little hard to see. What is the robot doing? In this case, where it starts with its arm, minus pi over 8 angular radians, and the object starts falling plus pi over 8 radians above it.
It's kind of keeps that oscillating motion, but it makes like larger movements in the opposite direction each time.
It's making large, it starts by making a large sweep actually away from the robot, away from the falling object, comes back. Here's this light colored trajectory. It passes somewhere over here, and then this light colored trajectory ends up over here, and this is the robot waggling its arm back and forth to the right, and then right at the end, it catches the object directly overhead. Yeah. Underneath this light colored trajectory on the left, there are some dark trajectories that you can see starting to emerge over here. In these dark trajectories, the arm started minus pi over 8 angular radians, and the object was dropped minus pi over 8 radians. The trajectory is darkened because it started at minus pi over 8 radians. What's the robot doing in that case?
Waiting for the object to come because it's like where it is, should be.
Waiting for it to come. Maybe it already knows, and it's just wagging its arm over here. Again, it's showing off. It's pointing at the object. The old baseball player Babe Ruth, I'm going to hit the ball over there. It already knows it's showing us. Maybe. Yeah. Okay. Obviously, there's a lot going on in this figure. Let's talk globally. What does the C turn N tend to do on average? What does it cause the robot to do, regardless of the initial angle of its arm and the initial position of the falling object? What's the robot doing?
It always starts by rotating to the left.
It always starts by rotating to the left. Yeah, so in all these cases, it always does the same thing. And then gradually it starts to do different things. What else can you tell me about what the C turn N is doing?
It has these 4 different ways that it can just like get to this point where it like squiggles in place.
It's not doing a unique set of actions in every case, right? There seem to be these like groupings of things that it does. It's almost like it's classifying the object. It's going to fall far to the left, or just a little bit to the left, or just a little bit to the right, or it's falling, or it is at the moment far to the left, or a little bit to the left, or a little bit to the right, or a lot to the right. It's kind of what it looks like. Any other observations? It's waving its arm like crazy in all these cases, right? It doesn't necessarily need to do this. We didn't program this into it. Why might it be doing that? Again, it's hard to say, but
it might be differentiating between the signals that its arm gives and the object gives.
The objects always fall. The objects are not waggling back and forth as they fall. The objects are falling in a straight line. Might be a vertical or diagonal line, but they're falling straight. Imagine the robot sort of moved its arm in the same way that it was detecting the object falling. Yeah? From the robot's perspective, it would have a hard time knowing which is which, right? So a good strategy in general is do something with your body so that the sensory repercussions of your actions are very different from the sensory repercussions you get from actions of other things out there in the world. This is a generally good strategy for learning to distinguish between self and non-self. Yeah?
Just thinking like in terms of like how we determine self and non-self, like we tend to have a sense for where body is in space, and it can also like to a certain extent have touch on our extremities. Is there a reason not to just give the robot this is the X, Y, or theta angle of your arm and instead force it to rely on it seeing its own arm?
You could. We could make things easier on the robot and give it the angle of its arm, but that's not the goal here, right? Again, we're trying to do a minimal experiment, and we want the robot, or we want to see whether evolution can evolve a behavior for this robot. In a lot of these experiments, they're intentionally making things hard on the robot. Of course, we could give it a lot more sensors, a lot more information, and make the discrimination between self and non-self trivial. You mentioned in our case that we have a sense of where we are in space. That is not an innate sense. That is something we learned as infants through a lot of our actions. It's not trivial. There's a reason that infants and toddlers are thrashing around like crazy, grab everything within reach, put stuff in their mouths. They're learning a lot of these things. Where do I end and where does the world begin? It's not trivial. So far, so good? Question?
Why, in the two cases in the middle where it's like the squiggles in the middle, why is the black one on the right and the whiter one on the left when it's like the opposite of where it is?
Good question. So if you visually parse this figure, there are some cases in which the object is approaching from the right and the robot is waggling its arm to the left, or the object is falling from the left and it's waggling its arm to the right. And there are other situations, like here, where it's waggling its arm in the direction in which the object is approaching. Why do these two conditions exist? I have no idea. Who knows? You can imagine evolving this all again and plotting this whole thing again for a different CTRNN evolved from a different population. Do you get the same pattern? Do you get something different? In your final project, that's one of the fun things to do. Do you get what's known as convergent evolution, meaning evolution always hits on the same strategy? Or do you get divergent evolution? Yeah. Eyes have evolved on planet Earth, 7, 8, I forget what the number is. A lot of times, eyes are very different. Mammalian eyes are very different from octopi eyes. They're completely different solutions, divergent evolution. Legged locomotion has evolved in mammals, birds, reptiles, other species. Generally speaking, except that the direction in which our knees point, the general strategy for moving using legs is kind of the same across species. That's convergent evolution. Evolution seems to hit on the same solution over and over again. Whether this particular behavior is the only one that works, and if you run evolution again, you'll get something the same, or maybe there are other solutions that can evolve, it's not clear. Could be a good thing to try in a final project. Other questions? Okay. All right, let's move on to the third building block. I asked you about cog this morning. I was pushing on your short-term memory. Can you remember all the way back 2 or 3 weeks or maybe 4 weeks? Yeah? Not easy to survive in this world if you can't remember what mistakes and successful things you did in the past. Yeah? So they're going to test the robot's ability to evolve short-term memory, and they're going to do it by hobbling the robot. We're going to go back to our Space Invaders robot. This is a robot that is able to move left and right along the bottom of the screen. So we're back to two motors. Again, the robot has 7 proximity sensors that report the length of these beams. They're drawn as dashed lines in this cartoon figure to represent that the moment the robot starts moving, it goes blind. The sensors shut off. So this robot is also partially blind like cog. It can see perfectly well as long as it doesn't move. The moment it starts moving, it can no longer see. If it stops moving again, it still can't see. Its eyes never open again. Yeah? You're going to drop a single object that might fall straight down, might fall diagonally, might fall slowly, might fall quickly. The robot's got to see the object, figure out whatever it needs to figure out in the CTRNN, and then start moving so that its horizontal position is the same as the horizontal position of the object when the object gets to the ground. Make sense? Okay. I think in the interest of time, we'll skip over the fitness function. It evolves for the robot to catch the object, be at the same place as the object when the object gets to the ground. Similar picture to what we've seen before. They took the most fit CTRNN at the end of the evolutionary run, played it back under a whole bunch of different environments where the final object could hit anywhere, any horizontal position at the bottom of the screen. And the vertical axis represents the horizontal position of the robot at the bottom of the screen at that time. How does the robot do? I see some thumbs up again. Generally speaking, whatever the final position is of the object, that is also the final horizontal position of the robot. Most of the time, it's where the robot is where it needs to be. Not all the time. Where is it making some mistakes?
When it's already in the right spot.
When it's already in the right spot, yeah, absolutely. The object, wherever the object started, it's going to hit bottom center, and the robot isn't exactly there. It's a little bit to the left or a little bit to the right. Yeah.
Could it be because it's not passing through as many of the sensor beams?
Possibly. Why does it make a mistake in the center here? Let's have a look again at this figure, which is showing what that evolved CTRNN causes the robot to do, how it causes the robot to move in a bunch of different conditions. We're going to look at 1, 2, 3, 4, 5, 6, 7, 8, 16 different environments. At the top of the screen here, like we saw in the first experiment, it's reporting the horizontal position of the object relative to the robot. So upper left, up here, the object was placed above and to the left of the robot. Upper right in this figure, the object was placed above and to the right of the robot. And all of these objects start falling directly vertically. They're all falling straight down, which is represented by these lines here. What are the diagonal lines telling you? What's happening? We're evaluating this CTRNN in 16 different environments. The object starts at some different horizontal position at the top of the screen. The object always falls straight down. What's happening? The robot starts moving. So a diagonal line is representing that the horizontal position, it should probably say the horizontal difference between the position of the robot and the horizontal position of the object is changing. Yeah? Most of these lines converge at the bottom at 0, meaning the horizontal difference between the horizontal position of the robot and the horizontal position of the object is about the same. The difference is near 0. So the robot is more or less catching the objects in all of these cases. What strategy is the robot using here? How is it catching these objects?
It seems to know how long it'll take to get somewhere, and it leaves at the last possible moment so it gets there right on time.
This is the lazy robot, right? It moves at a constant speed. It's not waving around or jiggling back and forth. It moves at a constant speed and gets there exactly when the object hits. Yeah? The robot always moves at the same speed. All of the slopes of the diagonal lines here, all those slopes are the same, the absolute values of the slopes. Yeah? So it never hurries, it never dawdles, it always moves at the same speed. The only thing that differs for this robot in these different environments is the time at which it starts moving. Everybody see that? Kind of interesting. They've colored the trajectories here based on whether the robot did a good job or not. So you can see the black lines are all converging almost exactly at 0. The gray lines, the robot kind of missed. It was a little bit to the left or a little bit to the right. They put that in, that is additional detail in to give you a hint about what this robot is doing. It's a pretty good strategy, right? But there's something that's still not quite right here. What is it? What's common among these gray trajectories? Why do you think it's making mistakes in these 1, 2, 3, 4, 5, 6 different environments?
Is it waiting until the object passes out of its field of vision to move?
Looks like it, right? At least in the 2 leftmost and the 2 rightmost trajectories. If you think about this cone of perception, it doesn't take long for objects that are very far upper left and very far upper right to pass beyond the robot's ability to see. So it's not blind yet. It can see, it just can't see the object. Yeah? So the robot has a very small window of time in which to make a decision, quote unquote, make a decision about what to do. And it's doing pretty well, but not perfectly. Yeah? So that's kind of expected. That makes sense. What about these 2 in the center? It's being a little bit too lazy in these cases, right? It chooses never to move.
Do they never leave its field of view?
They never leave it, so it's seeing the object. It's not really clear what's going on here. This case is very similar to this case. Who knows? Again, evolution is a satisficer, not an optimizer. Yeah, it's not perfect, but okay. Okay, they took the same evolved CTRNN. Now they dropped a whole bunch of objects that fell at diagonals to the robot. What we just saw were objects that were falling straight down. And again, we have on the horizontal axis final object position. Where did it hit at the bottom of the screen? Where did it hit at the bottom of the screen? And then the final angle position. Where was the agent at the bottom of the screen when that happened? How is the CTRNN enabling the robot to do in this case, or these cases, diagonally falling objects? It's not bad, but not great, right? These points are not clinging to the diagonal here as well as they did in this case. These environments are more alien to the robot. The robot never saw diagonally falling objects during evolution. So we're exposing it to something it's never seen before in general. It's still doing more or less the same thing, but having a harder and harder time of it. Yep. Okay. Again, let's see what it's doing. So same throughout all these plots, we're looking at one evolved CTRNN, the one that was the best from evolution. They're going to drop a whole bunch of single objects from the top of the screen, and they all fall at the same speed, and they fall at the same angle. Take the same CTRNN, drop a whole bunch of objects from top center of the screen, but they all fall along different diagonal trajectories. What does this evolved CTRNN cause the robot to do in this case? It's doing something different than what it did in these cases. What's the difference here? What's the difference in the robot's behavior between this and this? It's zigzagging, right? The robot is reversing direction. It's moving, which means it's blind. All the seven proximity sensors are reporting 0 all the time. It seems like it's sweeping, underneath the object to figure out where the object is going to hit, but it's blind. Nobody knows why it's doing this. It's inexplicable. Again, something you see in naturally evolved species. We do surprising things under certain conditions. Not necessarily good, not necessarily bad, just is. Okay, we've got 7 minutes left, so we may or may not make it through the fourth and final experiment in this series. This is arguably, for these minimal robots, one of the hardest things to do, and also arguably one of the hardest things for humans to do, selective attention. Hopefully, for most of the last hour and 15 minutes, I've had most of your attention. However, you may have your smartphone on vibrate, and from time to time you might feel your phone vibrate, and you might start thinking, who's calling me at 8:30 on a Thursday morning? It's probably my mother. No, she's not up yet. Who else could it possibly be? You might surreptitiously check your phone to see, and then you come back to lecture mentally, and you've got to remember what it was we were talking about. Are we still talking about short-term memory? Have we moved on to do something else? Throughout your day, you have to select what to attend to. The tragedy of the digital age is there are a lot of things that are trying to pull your attention away from whatever it is you're currently attending to. There are thousands of experiments now in the literature about how humans do or how humans do poorly at dealing with switching your attention more and more at a higher and higher frequency throughout your day. Yeah? You all obviously have had this uniquely modern experience, right? Very tricky. Very tricky to come back and remember where you are and continue on. Yeah? Unfortunately, in the real world, we don't have the luxury of monotasking. Out in the wild, you cannot focus on chasing down a good piece of fruit and choose to ignore any potential predators in your environment. You have to, from time to time, switch what you're doing and what you're attending to, and that comes with a cost. You've got to remember and be able to come back. How difficult exactly is this for robots? This experiment was designed to test this. Yeah. We've got our Space Invaders robot like before, 2 motors. It's going to shuttle back and forth, left and right at the bottom of the screen. Again, we're going to drop a pair of objects, but these objects are not welded together. They can fall at different speeds. You'll see the length of these dashed arrows are longer. Some are falling faster than others. They're falling at different directions. And we're going to start these objects at different heights towards the top of the screen. So at the beginning of every simulation, of every evaluation, one of the 2 objects is going to be closer to the robot. Yeah. What do you think the robot has to do? What are we going to evolve the robot to do in this situation? We've got independent objects falling at different speeds and angles.
You gotta catch both.
Got to catch both, right? So they are going to hit at different positions at different times, and the robot has to be at both those places at those times. Fitness function isn't that complicated. Kind of makes sense. Yeah. Why is this hard? What makes this hard for the robot?
Well, for one thing, it has to remember where the other one was because the sensors are pretty limited in range. So like when it's going to catch the other one, it's not going to know where the other one was. It has to like remember its trajectory and go to that. Absolutely.
So in this little cartoon here, it's actually not clear. This one is close, so maybe the robot's got to go chase after this one. But this object, which is further away, is falling faster. The dashed black line is longer. Yep.
Sorry, when it starts moving, does it like lose its vision?
No, things are hard enough for this robot.
Okay.
This robot can see and move all the time. Yep. Let's say it decides to go after the leftmost one. Its cone of perception may move enough to the left that now it can no longer see the one that's on its right. It at least has to remember, was the other one to my left or to my right? What else makes this task difficult?
Maybe determining which one to catch first.
Absolutely, right? Again, this cartoon was drawn deliberately to show that. The further object at this point in time may actually hit before the closer object. Yeah? Okay. I had a student a number of years ago now actually did this as a final project. So here's a robot succeeding at selective attention. Here's that case. The further object is moving faster. Selective attention is difficult for a lot of reasons. One is obviously that you're just changing your attention from time to time. One of the hardest things about selective attention is what do you switch your attention to? There's a bunch of issues or situations out there in the world that are demanding your attention. How do you know which one you should switch to next? Which situation should you donate more of your attention to? Hard to know, actually. And obviously that decision might change from moment to moment, as more information comes in. All right, I think this is a good place to pause for today. You have a quiz due tonight. Undergrads, you're working on 5. Grads, 9 and 10. Have a great rest of your day.